Hello. Hello. Okay. Good afternoon and welcome to this post-lunch session of today. In this session, we have two speakers. First, I'll invite Professor P.K. Panigrahi from ISR Kolkata, and he will be talking on PT symmetry in optics, exceptional points, and bound state in the continuum. Okay, Professor Panigrahi.
First of all, I am thankful to the local organizers, Bhavani and others, for giving me a chance to present our work here. So I would, from the very beginning, I would say that I am not a person who works in optics. But the fact that the Helmholtz equation and the Schrodinger equation have such a close similarity, so I found certain phenomena in optics, particularly very recently they pointed out light stops at exceptional point. So that is a physical later paper in 2018. That really drove me to this work. So what you will see is essentially, an explicit example, namely that of scarf 2 or the post-Taylor potential, which apparently has been realized in, optical systems like a refractive index recently, where all these phenomena, what we see, the exceptional points, the so-called zero-width resonance, namely bound state in the continuum, they explicitly manifest. So I was actually sort of, two of my motivations was one to see what is the meaning of this light stops at this exceptional point, where does it come from? Secondly, there were this mode of levels, that you hear when you go from this real spectra to complex conjugate pairs, you find merging of levels. That sort of intrigued me, that what is the group theory behind it? And it's amazing I found that this scarf 2 or the post-Taylor potential has all those things built in. So, and this work I have unfortunately I have not put the names of my collaborators. Both there are three works. Two of them are based on Annals of Physics papers published with Kumar Abhinav, and third one is just there in the archive. Okay. So as usual, I will start with a little bit of introduction to PT symmetry. For you, it is not no need, just for the sake of continuation. And then I'll get into the scarf 2 potential and first point out the, this spectra and what is the meaning of this, what are the parameters which characterize spontaneous breaking of PT symmetry. Then I'll point out that a very nice conserved quantity which comes here automatically, which this piece of work came out with Kumar Abhinav. And what this conserved correlation implies a lot of interesting things which was earlier observed in optics, but not completely explained. So the meaning of that, particularly for the scattering states, will be pointed out. And its implication towards scalar product. And recently, its implication for this light stops at exceptional point is the one which I show the connection to this. Then very intriguingly, earlier we had found, and this was also found independently by Professor Khare and his collaborators, there's this KdV, modified KdV, they have soliton solutions which are intrinsically PT symmetric, particularly for KdV. And why is it PT symmetric is not clear to me, but you demand that they solve the KdV equation or modified equation, they come out. And very intriguingly, as you know, this scarf 2 potential has connection with KdV. The so-called isospectral deformation has all the solutions of KdV can be obtained from the isospectral deformation of the scarf 2, which is one of the potentials. Now you will find that this thing, whatever I will be talking about, PT symmetry has intriguing connection with KdV also. So now, as you know, that this canonical commutation relation remains invariant if you take x2 minus x, p2 minus p, and i2 minus i. So this is the PT symmetry. And this Hamiltonian, people have talked about the simplest Hamiltonian. You redefine, get real spectrum, yet the Hamiltonian is not explicitly Hermitian. Just for the students, if you look at the function, it's a Gaussian shifted by some imaginary part. If you do a Fourier transform, you know that imaginary shift becomes real. So a Fourier transform of a Gaussian is a Gaussian. So if x with minus I alpha becomes p with plus alpha, that implies that it is actually momentum localized. So at least for this Hamiltonian, this imaginary part physically is clear that if it is real, then it is localized in the real space. If it is imaginary, it is localized in the momentum space. So now, but for other cases, this kind of interpretation is not very clear. So one tries to find out independently for each of them what the meaning of this complex potential. So now I will not get into it. As you know that when the spectrum is real, there is this possibility of defining the norm which exists, and that brings in this eta thing. For matrices, Das and his collaborator have given it. In general, they have been studied by Bender, Mostafazadeh, and others. But when it is complex, where the energy appear in pairs, still that problem remains unsolved. And so generally, if we go to this optical problem or quantum mechanical problem, optics is Helmholtz equation where you have refractive index, which are designed in this way. And they are actually gain-loss balanced medium. You see any experimental realization, you will find there is a symmetry point across which one side there is a gain, other side there is a loss. So this gain-loss balanced medium is the one which gives rise to PT-symmetric systems. So there is an even part and there is an odd part with an I. So odd under x goes to minus x, pulls out a minus sign, goes to I minus I. This remains intact. So that is the PT symmetry of the Schrodinger equation or the Helmholtz equation as the situation may be. Now, so as I promised to you, let's look at this potential which was realized early on by quite a few people, that this is a very explicit example. And interestingly, this kind of potentials appears in nonlinear Schrodinger equation where the psi mod square psi in the soliton sector can give rise to this kind of potential. And interestingly, it always gives you only PT symmetry. So why only PT symmetric phase is not clear, but in LSE with a soliton sector, you do get this kind of potential, but again with PT symmetry. So now, first of all, some parameterization. So I will actually, you will see this thing which I'm alluding to, namely merging of levels at the exceptional point, becomes clear because this class of potential can be factorized in two different ways. You'll find always there will be two superpotentials giving rise to a given potential. And these two superpotentials give rise to two representations of an underlying SL2R or SL2C symmetry. And because the potential is unique, these two representations give rise to representations of this potential. And when they will merge for at specific points. I'll show you coming from here, you will realize an exceptional point. So let me first parameterize this thing properly. It has been done keeping in mind the symmetry aspect I'm talking about. So you put in a very nice, peculiar way. You may wonder why. But you see tan hyperbolic I'm putting with a real parameter and ICPT and with sec with an I. You will see why it is. So if you find the potential, just W square plus W prime, derivative of W, put H bar is equal to 1, very complicated looking, then you demand PT symmetry. Very interestingly, it comes out in a composite condition of this kind. There's a product of this parameter CPT and some other thing is equal to 0. So you see, it can become 0 when this is equal to 0. That happens when you are in the PT symmetric phase. I'll show you explicitly how. When this is 0, that will happen when in the PT broken phase, spontaneously broken phase. When both of them is equal to 0, that is the phase where that is exceptional point. And you will find out that from the real side, there are two representations which will come out from here. Complex conjugate side, there will be two representations coming from this plus minus sign. They will merge exactly at the exceptional point. So this parameterization is quite nice to understand the group theory behind it. So now let us see how exactly. So you solve it explicitly. Now let's go to the phase which is PT symmetric. So PT symmetric is CPT is equal to 0. So here it becomes very nice. Tan hyperbolic is odd. So there's a real part. This fellow is an I. Now the potential is explicitly PT symmetric and you solve explicitly. Eigenvalues are real. And here is your wave function. So no surprises, PT symmetric phase. Now fortunately in this case, when CPT is not 0, that means you are trying to go to the broken PT symmetric phase, then you demand this condition. Here also explicitly you can solve. Looks a bit complicated, but very nicely for this wave function, you get explicitly complex energy. You see the energy and they occur in pairs. So that plus minus is the one which I was referring to. They give rise to these pairs. They correspond to two representations of an underlying SL2C symmetry. So very good. So now you see the wave function which has this exponential tan inverse factor. This is the factor which is responsible for this imaginary energy which comes out here. And say explicit example where complex conjugate energy appear by just solving out everything nicely. So now, and very interestingly here you'll find PT symmetry and supersymmetry gets very nicely interconnected. And this breaking of PT symmetry and supersymmetry also occurs in a very correlated manner. I'll show you why. Now, let us see, let's go to the PT symmetric phase again, and you will realize that this potential has a symmetry of A going to B minus alpha by 2. So the potential is symmetric, but the superpotential is not. In fact, corresponding to these two cases, there are the two superpotentials which give rise to this potential, and of course the energy will be different and the wave function will be different. Now, so explicitly here are the two superpotentials, and the superpotentials, as all of us know, will give rise to two different wave functions. Now these are the energies. Now the question is that which one is lower? These are the two energies. Which one is lower? That will decide whatever is the ground state. But both these fellows exist, and these are the ones which will coincide when they are the exceptional point. So the origin of two representations or wave functions merging comes from this fact that there are two superpotentials giving rise to same potential, and one of them, of course, is a ground state. All this analysis is true, and we have done it using supersymmetry and shape invariance, provided A greater than 0, B greater than alpha by 2. So now you may wonder what will happen in the other cases. So that is the case where the supersymmetry breaks. So you will find out that these are the parameter ranges. SUSY unbroken phase corresponds here, and all these domains correspond to broken SUSY phase. But very interestingly, in this phase, as you know, for example, these potentials, when you try to solve them, you go to the hypergeometric equation. In these domains, you will find the people who are familiar with this isospectral, this self-adjoint extension, you will realize that both the solutions of this hypergeometric equation are physical here. You cannot throw them out. Like in case of transition potential, the same situation arises. You have to choose one of them. So here, actually, you can choose them, and you will find out that when you choose it, there is a very interesting supersymmetry which is present here that saves the situation, and you can exactly find out using some extended supersymmetry, the eigenvalues and eigenfunctions here. So although they are broken in terms of the original fellows, in some reparameterization domain, you can still get the energy and eigenfunctions. They correspond to that, that regime, the so-called transition potential, which needs a special attention, and it appears right here where the supersymmetry is broken. So now, okay. So now let us go to this exceptional point. As I told you, that exceptional point, CPT is equal to 0. If CPT is equal to 0, you can immediately realize the complex energies were characterized by plus minus CPT. So they will coincide at this point. Now, from the real side, A is equal to B plus alpha by 2, both those representations which were differing because of this A going to B plus alpha by 2, they also will merge at that point. So that is the point where these two complex eigenvalues will merge and the reals will merge. So in fact, if you look at it, because our energy has a square root kind of singularity, so that branch point is the one where this merging occurs, and that is the exceptional point. More pictorially, here is the parameter CPT, and here is the real and imaginary part. So the merging happens here. On the real side, two fellows, complex side, two fellows, they will merge exactly at this point. So now, okay, so now let's look at this bound state in the continuum. Now you go to, for example, your complex spectrum, you will find out in case of complex spectrum, if you put A is equal to N alpha, you will find that the energy is real. You know that other fellow, the A is equal to N alpha, there was A minus N alpha, that part goes away, and there was ICPT with a minus sign, so that becomes plus. So you amazingly have real energy but positive. So as all of us know, these are the basically resonances, but zero width. There is no width. So this, if you look at the thing carefully in the literature, they are known as bound state in the continuum. They were originally investigated, by Wigner and von Neumann. So with the way they set it up is, the question was that can you have a potential where there will be reflection and transmission, but eventually, when you go asymptotically, the whole of the wave function will be reflected back, so that it will be a loose bound state. They have been observed, particularly in optical fibers and other situations, material systems with appropriately designed layer material. So they have zero width and they are very useful. You can have a loose bound state, oscillatory character, damped away to infinity. Now you'll find many of these quantum, image, memory devices, at least I had seen 2 of these examples, which rely on this, that you can actually store the information in this kind of wave function. You can manipulate them very nicely. You can physically move them around, and so they are quite useful. And here explicitly, if you see the wave function, you'll find all these properties which I'm mentioning, they are all present in that wave function. So we have an explicit example where you will find this occurs. So now they are deep inside in the complex parameter domain, and only specifically A is equal to n alpha. Now, fortunately, when you analyze, these things were known earlier. If you go to scattering matrix and look at the zeros and poles, these things you get information from there also. But here it comes out very explicitly. Now, so now let us look at this broken phase a bit more carefully. So just for the sake of completeness, that this is, you start with CPT not equal to 0. So here are these things, and as I told you, when A is equal to n alpha, this flow goes away, and this plus minus merges. So I square gives you minus, so it's positive energy. And the corresponding wave function, if you go back, you'll find that the corresponding wave function has an oscillatory character. So fine, these are basically like engineering kind of thing with an explicit potential. You find all those things nicely. But if you go back, if you just think for a moment, you will find out in case of normal Schrodinger equation with a potential V, which was real, we took the Schrodinger equation, took its complex conjugate, subtracted it, we got the correspondingly d rho by dt plus divergence of j is equal to 0, the conservation law. You try the same thing here, because the potential is pretty symmetric. You can do some trick. You can check explicitly that psi star minus x psi, this thing will be conserved. You can actually set up a continuity equation involving psi star minus x and psi of x. Now this obviously is a non-local thing because psi of x and psi star minus x. But if you see the, so the conserved quantity or the conserved density is this kind of correlation. Now if you see physically, you see most of the material which they design, they will have always a symmetry point around which loss and gain kind of things will be effectively balanced. And physically, intuitively, it is actually related to that. But anyway, for this kind of potential, you can generally have these kind of conditions. Now, this has implications both for bound state and real state. Now, I will not do the analysis carefully, but if you do the analysis carefully, looking at the incoming and outgoing waves, now you will find out because of that condition, if you look at this type of when you go to asymptotic fields, expand in terms of plane waves, particularly for sec hyperbolic thing, you can do that because the potential imaginary part of that goes to 0, real part becomes a constant. So you have a plane wave expansion. You can actually read them like incoming and outgoing plane waves, so where you can do all the scattering. When you do that, you find that there are conditions this S matrix must satisfy coming from this kind of conservation. So the condition is, this kind of condition was there, in this optics people had written down this thing in condensed matter. This was observed in 1997 by Binakar and co-workers in certain systems, that these kind of conditions were arising. But here, it arises explicitly because of this conservation law which comes out of the system. Now, you will find that S matrix is not unitary, but it is Hermitian. So now, from here, you can also, when the energy eigenvalue is real, you can actually find this so-called eta operator, which is the norm. So all this analysis is there in our Annals of Physics paper, Kumar Abhinav and myself. Now, furthermore, if you look at the odd part alone, you find, this kind of condition is satisfied. That S dagger B or S minus B or is equal to identity. So, and this is in general, this kind of duality was earlier known in case of optics and also condensed matter system, but it comes out nicely here. And for this case also, you will find that this thing is satisfied, but it's a special example. Now, as expectedly, when you look at the reflection transmission coefficient, you find that flux is not conserved because of these additional terms which are present here. It is not expected. Now, only when that B is equal to 0, so you get back your flux conservation. When the, in the conserved, when you are in the PT symmetric phase, you can actually invoke that eta norm and deal in terms of a rigged Hilbert space. I will not get into it. But the other side, still the norm question is not settled. Okay, so now how do you get the norm? what you find, if since the bound state energy is real, you can actually, that psi star minus x, you can write as psi of x. So then this fellow becomes, modulo that additional phase coming from the energy, this becomes psi square. Now you will find that this observation had played a key role in the, in that light stops at exceptional point. So here, this is the norm that this is actually psi square, this norm is psi square, that actually plays a key role. Okay, so now, so this is basically a bit more of, formal analysis, no need to get into that, but all those things are there. So basically the norm, I'm trying to show how the norm will come. So no need to bore you, but eventually in the bound state case, if it is energy is real, you do define a norm and that comes out nicely. This is more interesting. This one, as this 2018 physical regulator paper, they took this Helmholtz equation and looked at a PT symmetry condition, and they found out that at the exceptional point, this flow goes to 0, psi square goes to 0. So, and from general analysis, assuming the energy eigenvalues are only real, they could come up with that the group velocity will go to 0 because this goes to 0. So in fact, what we showed is that this is a general property of the system, and it arises because of this conserved, correlation that goes to 0 exactly at the exceptional point because of a branch point similarity. So now, so you can see the usefulness of this general conservation law. Now, as I told you, very mysteriously, this KdV, modified KdV kind of equations appear here. Now you see this, there are two superpotentials giving rise to the same potential. They differ by a phi, and this phi explicitly given like this. Now you can actually check that this is actually an isospectral deformation. Why is that? Because the spectrum is same, potential is same. So this is an isospectral deformation with a parameter condition. This parameter condition is the one which came from the symmetry which I had mentioned to you. Now once the parameter is satisfied, you find this phi, which is like the superpotential part, satisfies the modified KdV equation, and correspondingly the potential satisfies the KdV equation. So this, it's not unexpected, but this symmetry and appearance of this, integrable equations is still positing. I'm not very clear that these systems are usually associated with, quite a bit of symmetry. Now, how that is coming up here is not completely clear to me, but they do appear. Okay, so this experimental part people have talked about earlier in the Helmholtz equation. This gain-loss balance medium is the one who is the deal with, and they're looking at the light propagation. People have shown early on in 2009, and later on is the Helmholtz equation, and refractive index is the one who is the deal with. So now, yeah. No. There are here two superpotentials giving rise to the same potential. Two superpotentials, W2 and W1, giving rise to the same potential. Now, depending on the parameter values, the energy could be different. Okay. Now, when this satisfies the modified KdV equation, so the energy is coincide. That is the condition. So it is actually isospectral deformation. That isospectral deformation, that is how originally one used to generate solutions of that. So under the isospectral condition, you find it satisfies modified KdV equation. Okay. And the potential will satisfy the KdV equation.
Okay. And that is integrable or not? Huh? Is the modified KdV integrable?
Yeah, it is integrable. KdV, modified KdV, both are integrable.
Right, but the modified is also integrable.
Okay. MKdV is not to be integrable. First was KdV, then modified KdV, modified KdV is not to be integrable. Yeah. That, it has nothing to do with that, conserved correlation. Conserved correlation had implication for, this S matrix and additional conditions which are coming up in optics and convex matter system. They appear because of this conserved correlation. And the wave function becoming 0 at that psi square, that norm becoming 0 at the exceptional point, which is responsible for the group velocity, just light stopping. Yeah. And this system actually has been, realized in, by this Gopal, our faculty there, Swashish, Dr. Gupta, Professor Agarwal, they are co-authors. So there's a patent on this. So these potentials have been realized experimentally, yeah, in optics. So anyway, I will not go into it, but main thing is that optically these things are realized, And what I was mentioning about these S matrix poles and zeros, how they move around when the parameter changes, experimentally they have been seen. So people who are interested, they can get into it. There is something called CPA Laser. There was this conditional transfer matrix, as you will see, if somebody goes through our paper, you will see that conserved correlation gives rise to this also. This basically implies that unlike normal scattering, here you should have both incoming waves and both outgoing waves. It is essential to have this kind of laser, and a PT symmetric laser cannot be possible without that kind of condition. So that comes because both the things have to be present. Okay. Basically, yeah, both outgoing or both incoming, they have to be present. Otherwise, this is not possible. And that comes from there. Now again, a little more about this KdV business. That so why, if you go to KdV or modified KdV, so very interestingly, you will find, there are two kinds of modified KdV equations. They differ by a sign here. For both the cases, you will find solutions. Of course, a bit there will be, they go to each other under this kind of condition. V goes to IV, and as you know, the Miura transform connects KdV to modified KdV. So integrability of that actually you can establish through this Miura transform. Now, interestingly, the solutions what you find are this type: Cn square plus ISNDN type of solutions. And this one is again, Sn is odd, Dn is even, so plus or minus, and this is again PT symmetric. So you always find PT symmetric solutions for KdV equations. Modified KdV, they will PT breaking because it is actually linear, whereas this U is like V square plus V prime. So for the KdV equation, you find PT symmetric solutions, and a variety of equation solutions you can write down. Some of them have a very interesting property that in this modulus parameter, in one range, they will be going around one direction. In the other range, they will be going in the opposite directions. And exactly, there will be no solution when m is equal to half. So this kind of thing, appears in case of a nonlinear Schrodinger equation also, where m is equal to half, there is a phase transition taking place, from both the regimes. So there might be some deeper connection here also, because as you know, KdV appears in fluid dynamics. So the physical meaning of these kind of things I have not explored. And as you know, these have deep connections with theta functions and other things also. It remains to be explored. There are, particularly in fluid dynamics, what is the meaning of these kind of solutions remains to be explored. Okay, so now more solutions, but always you find the same kind of thing. Here is a background, but again PT symmetric. Cn is even, Sn is odd, and there is an I sitting here. So, okay, so now you can actually then go to real case m is equal to 1. You find these kind of solutions. Very interestingly, this type of solutions appears in LSC and also in this Bogoliov-Dijen type of equation in superconductivity. So there, these kind of background solutions, one of them was being mentioned in the morning as solitons. They do appear as solitons. And there is some connection of this with Majorana fermions or rather Majorana modes. So these, kind of symmetries that people are talking about now are expanding into other areas of condensed matter. So hopefully, more remains to be learned from here. So modified KdV, linear solutions. But as you see, this is PT odd. For example, Sn goes to minus Sn, I goes to minus I. So this is PT odd. And appears in both the sectors, but with certain conditions on the this modulus parameter. Not in general true. Okay, more solutions of this kind, again PT odd. So anyway, so let me conclude. So main point is that PT symmetric systems are appearing both in optics and quantum mechanical systems. Because of the PT symmetry, there are certain inherent restrictions on the S matrix. Now, in optics, the consequence of that there are these kind of strange lasers where you have both incoming and outgoing waves. So, and you have in fluid dynamics, like in KdV, modified KdV, these solutions imply certain kind of solutions where you have a modulus parameter in fluid flowing in one direction in one domain, flowing in the other direction, and exactly at that point, probably there is some kind of a phase transition. So there is, deep structure and mathematics remains to be understood here. So I will not get into more, but at least here is an explicit example where you see all those things nicely. So So I'll stop here. Thank you.
Yeah, can you please elaborate on group velocity of light, because it's not a single plane wave, is it? I mean,
definition which I had given is from the book, that derivation.
Yeah.
It is not it's basically the wave packet.
Yeah, it's a way, okay. Then that's relevant. I know, I just was confused. And then that's, of course, and it happens for all Ks, there is no wave vector dependence per se.
No.
Okay, thank you.
Any other questions?
So this is more of a comment than a question, but so I disagree with your definition of the bound state and continuum, because I think what you found, I agree it's a spectral singularity, but a bound state and continuum, it's defined as a localized state, right? It's a very particular localized state that exists in the continuum, which is kind of counterintuitive because it's localized, yet it's, among the scattering states. But what you've shown is something where the transmission and the reflection diverge. And if you write the wave function for it, it's an outgoing wave, and it exists inside the continuum. It's a kind of steady state solution. So for that reason, I think it's better to call it a spectral singularity, but not a bound state and continuum.
Actually, if you look at the wave function, I have given explicitly wave function. Maybe we can look at it later on. I have given explicitly wave function in the complex domain. There, if you put A is equal to n alpha, those wave functions are actually damped wave functions asymptotically with oscillatory character.
They're damped?
Because it's a this is a bound state. So the complex conjugate pair.
I guess I'm not.
Okay, what?
Okay. I think if I see a spectral singularity, I expect it to be an outgoing wave, right, with no damping, or a bound state that is confined. That's confined in kind of the scattering region.
Yes.
Potential region of the problem.
Yes.
So if it's damped, then I think your transmission and reflection don't diverge. They don't go to infinity, in which case it's not a spectral singularity.
No, what I will do, since, I'll get back to you. I have the wave function in general. There I will just go put A is equal to n alpha, look at that function. Okay, my bet is that function is a bound state kind of thing, namely it oscillates. See, bound state in the continuum are the loosely bound wave functions which oscillates and asymptotically goes to 0. At least that's what I learned from Wigner and von Neumann, that these are the waves, you have a potential, oscillatory potential, which asymptotically goes to 0. The diffraction and transmission.
The potential goes to 0.
Goes to 0, but the wave function also is localized at the origin. Slowly it damps up to 0. By power law, it goes to 0.
I guess in that case, I don't understand how your transmission and reflection diverge, though. Because to put it another way, I think in a Hermitian system where there's a bound state in continuum, I expect the transmission is probably 1 and the reflection is 0, whereas at the spectral singularity, they both diverge. So it really has to be one or the other. It can't be both.
Okay, so I look at it. Thank you for the comment. I look at it because I have the explicit wave function. I look at it. Thanks. Yeah.
Any other questions? So if not, let's thank Professor Panigrahi.